Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be discovering some of the strangest objects in the universe. Despite what you might see when you look at the night sky, not all stars are the same, and some are so strange and unusual that they seem to defy the laws of physics. Most stars look steady from afar, little points of light scattered across the dark. But as we explore them more deeply, the vast differences begin to emerge. There are some that pulse like beating hearts, some that spin so fast they throw matter into space, and others that aren't really stars at all, but remnants of something far more ancient. Some live by feeding on companions, while others erupt without warning. And some are so dense, so magnetic, and so extreme that they seem to belong to another realm entirely. Tonight's journey is a slow passage through these stellar oddities, these cosmic exceptions that reveal just how majestic the universe can be. The deeper astronomers look, the more mysteries they uncover. And hidden among those distant lights are objects that challenge what a star can be, how it can live, and how it can end. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your eyes to grow heavy. And let your thoughts wander upward as we explore our remarkable cosmos together. Let's begin. 1 teaspoon of a dead star could outweigh a mountain. When a massive star collapses after a supernova, its core can be crushed into a neutron star. The object left behind is tiny by stellar standards, often only about the size of a city, but the matter inside it is packed to an almost absurd degree. Gravity presses atoms so hard that electrons and protons are forced together, leaving behind a sphere made mostly of neutrons. The result is density so extreme that ordinary comparisons start to fail. A spoonful brought to Earth would weigh billions of tons. It would not sit politely in the spoon. It would punch through the ground with catastrophic force. Yet this impossible object is real. Some neutron stars spin rapidly. Some flash like cosmic beacons. Some carry magnetic fields beyond anything we can reproduce. They are what remains when a star loses its struggle against its own gravity and becomes something stranger than almost anyone expects matter can be. Some stars look impossibly young in places where all stars should be old. In ancient globular clusters, most stars formed around the same distant time. That means the brighter and heavier ones should have burned out long ago, leaving only older, dimmer survivors behind. Yet scattered among these elderly populations are stars that shine hot and blue, as though they arrived late to the party. Astronomers call them blue stragglers because they lag behind the normal aging pattern of the cluster. They seem younger than their neighbors, but they are not truly young at all. Most likely, they were rejuvenated. In crowded star clusters, close encounters are common. 2 stars can merge, or one can draw fresh fuel from a companion. That stolen or combined hydrogen lets it burn brighter again. Some rare stars are already shedding themselves into space before they die. Long before the final blast arrives, some of the most massive stars begin to come apart in full view of the universe. They cast off huge layers of gas through fierce winds and sudden eruptions, building glowing clouds around themselves while they are still alive. Wolf-Rayet stars do this with astonishing force. Luminous blue variables can do it in violent outbursts that briefly make them far brighter than usual. Eta Carinae is one of the most famous examples. In the 19th century, it erupted so dramatically that it became one of the brightest stars in the sky, yet it survived. What we see now is a great expanding nebula made from material the star threw away itself. These stars are not waiting quietly for the end. They are rewriting their own surroundings first, filling space with the ingredients of future shockwaves, future dust, and future worlds. As though the clock was turned back. They are stellar imposters hiding among ancient suns, and they reveal that even in old star cities, collisions, theft, and second chances still happen. A few stars pulse with such precision they rival atomic clocks. Some dead stars become pulsars, spinning neutron stars that sweep beams of radio light across space. If one of those beams crosses Earth, astronomers detect a flash each time the star rotates. The remarkable part is not just the flashing. It is the regularity. Certain pulsars keep time with astonishing stability, so steady that over long periods they can rival the precision of atomic clocks. Millisecond pulsars are the masters of this. They spin hundreds of times each second, often after being sped up by matter falling in from a companion star. Once that process settles, they become extraordinary cosmic metronomes. Their timing is so exact that astronomers use networks of them to search for faint ripples in spacetime itself. These stars are not bright because they are large or youthful. They are powerful because they are compact, fast, and uncannily reliable. A collapsed star can become one of the finest timekeepers in the universe. Some rare stars spin so fast they fling their own matter outward. Most stars rotate, but a few take it to such an extreme that their equators are nearly at the breaking point. These are often called B stars. They spin so rapidly that gas can be launched from the star's outer layers and spread into a flattened disk around it. The star is not exploding. It is simply turning with such speed that holding onto all its material becomes difficult. That spinning disk changes the light we receive, which is one reason these stars look so unusual through a telescope. Their shapes may also be distorted, with the equator bulging outward, while the poles remain hotter and brighter. In a sense, they are stars living on the edge of balance. Rotation becomes destiny. It alters their appearance, their behavior, and sometimes their fate. Instead of looking like calm, perfect spheres, they become restless objects, half star and half storm, wrapped in matter they could not quite keep. There are stars surrounded by shells they cast into space themselves. Some stars end their ordinary lives not with a giant supernova, but with a softer kind of grandeur. After swelling into red giants, they begin to lose their outer layers until those layers drift away into space. The hot core left behind lights the escaping gas from within, turning it into a glowing shell that can look like a ring, an eye, or a ghostly bubble. Despite the name, a planetary nebula has nothing to do with planets. It is the discarded atmosphere of a dying star, briefly illuminated before it fades into the dark. What makes these objects so captivating is their variety. Some are round, some are bipolar, some twist into elegant patterns shaped by magnetic fields or hidden companion stars. In the middle sits the exposed remnant, on its way to becoming a white dwarf. The star survives for a while, but only after casting off the very layers that once made it shine. Some stars survive by stealing gas from a companion beside them. In some binary systems, one star begins to age and swell until its outer gas drifts too close to its partner. Then gravity takes over, and the companion starts pulling that material away. What follows can be one of the most dramatic relationships in astronomy. A white dwarf can gather stolen gas into a hot, swirling disk before it crashes onto the surface. A neutron star can do the same, but with even more violence, producing fierce X-ray light. In some systems, the donor star is slowly stripped over time, losing mass to the more compact object beside it. These are not peaceful pairs. They are cosmic feeding arrangements shaped by proximity and gravity. Sometimes the theft triggers flashes, eruptions, or repeating outbursts. Sometimes it changes the future of both stars completely. A rare star in such a system is often not unusual because of what it was born as, but because of what its neighbor forced it to become. A few stars are the stripped glowing hearts of much larger suns. Not every star we see still wears its original outer layers. In close binary systems, one star can lose its hydrogen envelope to a nearby companion, leaving behind a much smaller and hotter object that would otherwise remain hidden. What is left is often called a stripped star, or in some cases, a helium star, because the deeper layers are suddenly exposed. These objects are fascinating because they reveal the interior of a star before the usual final collapse. It is like seeing the glowing engine after the casing has been torn away. They can be difficult to detect because the companion may outshine them in ordinary light, yet their heat and spectra give them away. Astronomers care about them for another reason too. They may be important ancestors of certain supernova and compact remnants. A star does not always need to die to reveal its core. Sometimes a partner uncovers it early. Some of the strangest stars may be halfway between star and explosion. Astronomers have found rare outbursts that look at first like supernova, yet the star seems to survive. These events are often called supernova imposters, which is a wonderful name because it captures the drama exactly. The eruption can become dazzlingly bright and hurl huge amounts of gas into space, but the core is not destroyed. Eta Carinae likely did something like this in the 19th century. For a while it blazed with astonishing intensity, then dimmed again, leaving behind an immense cloud instead of a dead remnant. These eruptions matter because they blur the line between ordinary stellar instability and final catastrophe. They suggest that some massive stars can lurch toward disaster in steps, shedding mass in giant fits before the true ending arrives. So the universe gives us a strange intermediate state. Not calm life, not full death, but a violent rehearsal that looks alarmingly close to the real thing. Rare stars reveal that the universe makes far stranger suns than ours. Our sun is wonderful, but in stellar terms, it is reassuringly ordinary. Rare stars show just how small a slice of possibility there really is. The universe can make stars that pulse, stars that cannibalize neighbors, stars stripped to their cores, stars wrapped in their own discarded layers, and dead stars denser than anything our everyday minds are built to. Imagine. Each one stretches the idea of what a star can be. More importantly, these objects are not merely curiosities. They help explain where heavy elements come from, how binary systems reshape stellar lives, and how extreme gravity, magnetism, and pressure behave in nature. The strangest stars are often the most revealing because they push physics into unusual territory. They expose hidden processes that ordinary stars keep quiet. Once you begin to notice them, the sky changes. It stops looking like a field of similar lights and starts feeling like a place full of wild exceptions. Wolf-rayed stars burn hot, fast, and live astonishingly short lives. These are among the most intense stars the universe can make. They began as very massive stars, but now they are in a late and ferocious stage where their surfaces are blasting outward in supersonic winds. Those winds are so powerful that they peel away matter at extraordinary rates, exposing deeper fusion layers that ordinary stars keep hidden. That is why their spectra look so unusual. We are seeing chemistry that usually stays buried far below the surface. They are blisteringly hot, often far hotter than the sun, and they waste very little time. A star that massive lives on borrowed time from the beginning, And this stage makes that urgency visible. It is all burn and no patience. These stars can carve glowing cavities in surrounding gas and flood their neighborhoods with harsh radiation. When one appears, astronomers are often looking at a star that is already racing toward one of the most violent endings in nature. Blue stragglers seem to have cheated age inside ancient star clusters. Imagine walking into a retirement village and finding a few people in the prime of youth, running laps while everyone else has clearly grown old. That is the puzzle these stars create. In globular clusters, the stars are ancient and should have aged together. Yet a few burn hotter and bluer than the rest, as though they were born much later. They were not. Most likely, they were renewed by close encounters in crowded stellar environments. Some are probably the result of mergers, where two stars collide and become one heavier object with fresh fuel. Others may have been fed by a companion that slowly poured mass onto them. Either way, the effect is remarkable. They stand out like counterfeit youth in an old stellar city. These stars are beautiful evidence that aging in the universe is not always a straight road. Sometimes gravity, crowding, and chance create a second life where none should exist. Magnetars are stars with the most violent magnetic fields known. If you took a compass near one of these objects, the thought experiment would end long before the compass mattered. A magnetar is a type of neutron star whose magnetic field is so overwhelming that it pushes physics into territory that feels unreal. It can twist the star's crust, stress the surrounding space, and unleash sudden flashes of energy that sweep across the galaxy. In rare giant flares, a brief outburst can release more energy than the sun produces in a vast stretch of time. The field itself is hard to picture because nothing in daily life prepares you for it. It is not simply strong. It is monstrous. It can dominate everything nearby and alter the behavior of matter in ways we cannot reproduce on Earth. These stars are not just exotic leftovers. They are natural laboratories for the most extreme magnetism in the cosmos, and they remind us how savage a dead star can become. Pulsars are dead stars that sweep space with beams like lighthouses. When a massive star dies and leaves behind a neutron star, the story does not always end in silence. If that remnant is spinning and has its magnetic axis tilted away from its rotation axis, it can send out narrow beams of radiation that sweep through space like a cosmic lighthouse. Each time one of those beams crosses Earth, astronomers detect a pulse. That is why pulsars seem to blink. They are not flashing on and off. They are spinning with astonishing regularity. Some rotate once in a second. Others whirl many times in the blink of an eye. These objects were discovered through radio signals, and at first the precision seemed so strange that a few scientists jokingly wondered if it might be artificial. It was not. Nature had simply built something more exact and eerie than anyone expected. A pulsar is the soundless rhythm of stellar death turned into a beacon, steady enough to map the invisible structure of space. White dwarfs are stellar cores left glowing after ordinary stars collapse. When a star like the Sun runs out of fuel for its final stages of ordinary fusion, it does not explode as a supernova. Instead, it sheds its outer layers and leaves behind a hot, compact core, dense and brilliant at first, which slowly cools over immense spans of time. That remnant is a white dwarf. It is no longer generating energy through the usual stellar engine, yet it still shines because of stored heat. What makes it extraordinary is the balance holding it up. Instead of ordinary pressure from hot gas, the object is supported by a quantum rule that stops electrons from being squeezed into the same state. That strange resistance keeps the star from collapsing further, even though the whole object is roughly Earth-sized. So here is a stellar ember, tiny by stellar standards, but carrying the mass of a star's heart. It is one of astronomy's most elegant endings, quiet, compact, and deeply strange. Neutron stars pack more mass than the Sun into a city. Take the mass of the Sun, then imagine trying to force it into something only about 20 kilometers across. The result is a neutron star, one of the most extreme objects that nature allows without making a black hole. Its gravity is fierce. Its surface is compact beyond anything ordinary language handles well. If you stood nearby, the difference in gravity between your head and feet would be catastrophic. Time itself would pass differently near such an object. Yet neutron stars are not just dense curiosities. They are the aftermath of collapse, the compressed core left behind when a massive star's outer layers are blasted away. In that remnant, matter is packed so tightly that the familiar structure of atoms no longer survives in the usual way. These stars can spin rapidly, emit radiation, quake, flare, and distort nearby space. They are tiny on the map of the cosmos, but in terms of physical extremes, they are among its most astonishing masterpieces. Carbon stars can become so rich in soot, they hide themselves. Some aging red giants change their chemistry in a dramatic way. Deep inside, fusion and mixing processes can bring carbon from the interior up into the outer layers. Once carbon becomes more abundant than oxygen, the whole atmosphere changes character. New molecules form, the star's light turns richly red, and carbon dust begins to condense in the surrounding gas. Over time, that dust can grow so thick that the star hides behind its own debris, dimming in visible light, while glowing more strongly in infrared. In a sense, the star becomes both actor and curtain. It makes the material that later obscures it. These objects are also important because they help seed interstellar space with carbon-rich dust, the raw material for future stars, planets, and chemistry. So what looks like a fading old giant is also a manufacturer of cosmic ingredients. It is a star ending one chapter by quietly filling space with the stuff of future worlds. Helium stars are rare suns stripped almost naked of hydrogen. Most stars spend the bulk of their visible lives wrapped in hydrogen because hydrogen is both their main fuel and their outer identity. Remove that layer and you expose something far stranger. A helium star is what can remain after a close companion pulls away the outer envelope, leaving behind a hotter, more compact object dominated by deeper material. It is a glimpse beneath the usual costume of starlight. These stars matter because they reveal stages that are often hidden, and because they may lead to unusual supernova that do not fit the familiar picture. In many cases, they are hard to spot, not because they lack power, but because they live in binary systems where the companion confuses the view. Yet their spectra betray them. They are evidence that stars do not simply evolve in isolation. They can be sculpted by partnership. A neighboring star can strip away an identity and leave behind a brilliant, exposed core. Some rare stars brighten only because they feed on a neighbor. Not every sudden brightening in the sky comes from a star generating more energy in its own core. In some binary systems, the spectacle comes from stolen matter. Gas from one star spirals toward a compact companion and forms a hot accretion disk, where friction and gravity turn infilling material into intense light. The feeding itself becomes the engine of brightness. Cataclysmic variables are a classic example. A white dwarf gathers gas from a nearby donor star, and the disk can suddenly flare when conditions change. In other systems, matter piles onto the compact star until a runaway surface event erupts. What makes these objects so gripping is that their brightness is not self-contained. It is the visible sign of a relationship, often an unequal and destructive one. One star loses. The other blazes. So when astronomers watch such a system brighten, they are often witnessing not a solitary transformation, but an ongoing act of cosmic dependence and theft. These stars were spinning disks of gas like fragile cosmic rings. These stars are rapid rotators, and that rapid rotation changes almost everything about how they look and behave. The outer layers near the equator are only loosely held, and under the right conditions, gas escapes into orbit around the star, building a flattened disk. It is not a solid ring like Saturn's. It is a shifting, delicate structure made of hot gas, and it can appear, fade, and rebuild over time. Through a telescope, this disk reveals itself in the star's spectrum, where emission lines announce that light is passing through orbiting material instead of only through a simple stellar atmosphere. That makes these stars especially intriguing because they are visibly dynamic. They wear evidence of instability. Some may also pulsate, and those inner tremors could help lift gas into the disk. So the whole system feels poised on a threshold. Rotation, structure, and light all interact, turning one star into something that looks half orderly and half unbound. Our coronae borealis stars can vanish behind clouds of their own carbon. Most variable stars change brightness in some predictable rhythm. These do something stranger. For long periods they may shine steadily. Then, without warning, they'd plunge in brightness, as though someone has pulled a curtain across them. The star itself has not gone away. Instead, it has formed a fresh cloud of carbon dust that drifts into our line of sight and blocks the light. Over time, that dust disperses and the star brightens again. The effect can be dramatic, like a celestial disappearance act performed by the star's own atmosphere. These objects are rare and deeply mysterious, not least because astronomers are still debating aspects of how they form. Some may be merger products, born when two white dwarfs combined. What makes them unforgettable is the sheer theatrical quality of their behavior. A star can spend years glowing normally, then suddenly hide behind matter it just created. It is a reminder that even old stars can still surprise the sky. Thorn-Titkow objects may hide a neutron star inside a giant. This idea sounds like something invented for science fiction, yet it comes from serious astrophysics. A Thorn-Titkow object would form if a neutron star ended up inside a red supergiant, settling into the core rather than destroying the whole star outright. From the outside, it might look almost ordinary, just another swollen giant star. But deep inside, the engine would be bizarre beyond comparison. Instead of a normal stellar core, there would be a collapsed neutron star, altering the structure and perhaps driving unusual nuclear processes. That could create strange surface chemistry, which is one of the few clues astronomers can search for. A few candidates have been proposed, though none has been confirmed beyond doubt. What makes this concept irresistible is its disguise. The most bizarre stars may not always look bizarre. One of the oddest objects in the universe could appear, at first glance, like a familiar red giant, while hiding an impossible secret at its center. Luminous blue variables can erupt without actually becoming supernova. These are among the most unstable massive stars known. Brilliant, hot, and living close to the limits of what a star can bear. At times, they become dramatically brighter and can throw huge amounts of gas into space, yet they survive the event. That is what makes them so fascinating. The eruption can look almost like a final catastrophe, but it turns out to be a violent episode rather than the end. Eta Carinae is the iconic example. Its 19th century outburst was so intense that it briefly ranked among the brightest stars in the sky, and the material it expelled still forms a vast glowing nebula today. These stars seem to live in a state of barely controlled instability, as though they are forever on the edge of becoming too luminous for their own outer layers to hold. They do not fail all at once. They convulse, shed, recover, and remain in view, each eruption a warning that something larger may still be coming. Some stars flicker because they are still struggling to be born. A newborn star is not born in a neat, clean moment. It emerges through struggle. Inside dark clouds, gravity draws gas and dust inward until a protostar begins to form, often surrounded by a disk and tangled magnetic fields. During this stage, the light can vary in irregular and fascinating ways. Material falling onto the growing star may arrive in bursts, making it brighten suddenly. Dust in the disk can drift across our line of sight and cause dips. Jets and hotspots can alter the signal again. So when astronomers watch certain young stars flicker, they are not seeing a stable star misbehaving. They are witnessing an unfinished object still negotiating its own creation. The process can take millions of years. Planets may be forming in the surrounding disk at the same time. This means the flickering is part of a larger story, not just of stellar birth, but of the chaotic environment from which whole planetary systems eventually emerge. Others shine strangely because two stars have merged into one. Sometimes the explanation for an odd star is not that it was born unusual, but that it became a single object through collision or merger. In close binary systems, orbital decay can slowly bring stars together until they coalesce. In dense clusters, direct collisions can also happen. The aftermath can be spectacular. A merger can create an object that is hotter, more massive, and more luminous than either parent would have been alone. It may rotate rapidly, display strange chemistry, or settle into a life that makes little sense if judged as a normal single star. Some unusual transients, called red nova, are thought to be the visible glow of stars merging in real time. For a brief period, the sky shows the act itself, not just the remade result. These events matter because they reveal that stellar evolution is not always a lonely path. Sometimes two histories collide and the universe writes a completely new one. A few stars pulse in several rhythms at the same time. Not every variable star beats with one clean pattern. Some oscillate in multiple modes at once, with different layers of the star expanding and contracting in overlapping rhythms. To astronomers, that is a gift. Each mode probes a different part of the interior, rather like hearing several notes from the same instrument and using them to infer its shape and tension. The result can look wonderfully complex. Brightness rises and falls in patterns that may seem almost musical, though the physics behind them is pressure, temperature, and structure. Delta Scuti stars and other pulsators can show this kind of mixed behavior, revealing that a star is not a simple glowing ball, but a layered object capable of many internal motions at once. When those motions are decoded, they offer a map of the hidden interior. So the flicker in the night sky becomes something far richer. It is not noise. It is the sound of a star resonating with itself. Some stellar remnants spin hundreds of times in a single second. Among the fastest objects in the cosmos are millisecond pulsars, neutron stars that rotate with astonishing speed and precision. These objects were not necessarily born spinning that fast. Many seem to have been recycled. A companion star fed matter onto the neutron star over long periods, and that inflowing material transferred angular momentum, winding the remnant up like a cosmic flywheel. By the time the feeding slowed or stopped, the neutron star had become a rapid rotator of extraordinary stability. Imagine something with more mass than the Sun, compressed into city size, turning hundreds of times every second without flying apart. That alone feels impossible, yet it is real. These objects are important not only because they are fast, but because they become exquisite tools. Their pulses arrive with such regularity that astronomers can use them to test gravity, study binary motion, and even search for deep background waves in space-time. Stellar death, given time and companionship, can become astonishingly elegant. The rarest stars often appear only in the briefest chapters. Part of what makes rare stars so compelling is not only how strange they are, but how briefly they remain visible in those strange states. Some phases of stellar life last millions or billions of years. Others pass like a spark. A massive star might spend a tiny fraction of its existence in a violently unstable stage. A merger remnant might show unusual properties for only a short interval before settling down. A star nearing collapse may expose a transient face that astronomers can easily miss if they are not watching at the right moment. That means the sky we study is full of timing. Discovery often depends on catching a star during a narrow chapter when its oddness is on display. Modern sky surveys have transformed this hunt because they scan huge areas repeatedly and notice changes that older astronomy could miss. In many cases, rarity is really the marriage of strangeness and brevity, which makes every detection feel like a successful ambush on time. Certain stars live fast enough to rewrite themselves in human history. Most stellar evolution unfolds far too slowly for a person to notice. Rare stars break that rule. Some have changed so dramatically over decades or centuries that their stories can be traced across written records, photographs, and modern instruments. Eta Carinae is the classic case, erupting so strongly in the 19th century that it transformed its appearance within human history. Other unstable stars have shifted temperature, brightness, or spectral type on timescales that let astronomers compare generations of observations and watch the changes accumulate. That is extraordinary, because stars usually feel like symbols of permanence. Here, instead, they become active dramas. A star can brighten, dim, shed material, or alter its outer layers in a time span that fits inside archives and observatories rather than only in theory. These are not frozen points of light. They are ongoing events. They remind us that the sky is not merely ancient. Parts of it are moving quickly enough for humanity to witness the rewrite. Some binary stars are locked in such tight orbits they touch. There are stellar pairs so close that their outer layers meet and mingle, forming what is known as a contact binary. Instead of two clearly separate spheres, the system resembles a shared structure with matter flowing and stretching between them. The stars orbit each other with astonishing speed, sometimes completing a full circuit in less than a day. Their mutual gravity distorts them into egg-like shapes, and their light changes rhythmically as they eclipse and present different faces to Earth. These systems are fascinating because closeness becomes the defining force. Heat can move between the stars. Mass can shift. Angular momentum can change the future for both objects at once. In some cases, the orbit may shrink further until the pair merges into a single star. So what begins as a duet may end as one remade object. The contact binary is a vivid lesson that in astronomy, intimacy is not sentimental. It is structural, unstable, and often fate deciding itself in public. Black Widow pulsars slowly strip and scorch their tiny companions. This is one of the most ruthless relationships in the sky. A Black Widow pulsar is a fast-spinning neutron star paired with a much smaller companion that is slowly being destroyed. The pulsar blasts out radiation and a fierce wind of particles, heating the little star until its outer layers begin to stream away. Over time, the companion can be whittled down to a mere fraction of the Sun's mass. In some systems, it may vanish almost completely, leaving the pulsar alone after consuming the evidence of the partnership that reshaped it. These objects are thought to begin as X-ray binaries, where the neutron star is spun up by stolen gas. Once the feeding phase ends, the pulsar turns on like a weapon. What was once a source of nourishment becomes the target. It is a grim and fascinating inversion, a stellar survivor finishing the work by eroding the neighbor that once helped revive it. Redback pulsars do the same, but with heftier neighbors. If Black Widow pulsars are the lean assassins of binary astronomy, redbacks are the same basic idea with a sturdier victim. The companion in these systems is larger and more substantial, often still close to a normal star rather than a nearly exhausted remnant. That changes the drama. The pulsar's wind and radiation still batter the neighboring star, heating one side and driving matter away. But the battle feels more balanced, at least for a while. Some redbacks even appear able to switch states. At one time, the neutron star may be feeding from an accretion disk and shining in X-rays. Later, it may behave like a radio pulsar, blasting the companion and shutting off the inflow. That transition is thrilling because it lets astronomers catch binary evolution in motion, rather than only infer it afterward. A redback is not just a strange pair. It is a system caught mid-argument, with identity itself flickering between hunger and attack. Cataclysmic variables flare when stolen gas crashes onto white dwarfs. In these systems, the compact star is a white dwarf, and the fuel for the show comes from a nearby companion that has wandered too close to its gravitational grip. Gas spills away and forms a bright accretion disk around the white dwarf, circling faster and faster as it spirals inward. For a while, the system may glow with a kind of unstable calm. Then the disk can suddenly change state, dumping extra material inward and causing a dramatic rise in brightness. The whole system flares, sometimes by many times, before settling back again. These outbursts are not random fireworks. They are the visible result of matter piling up, heating, and surging through a delicate disk that cannot stay balanced forever. What makes them so gripping is that the star itself is not newly alive. It is an old remnant made spectacular by what falls onto it. Stolen gas becomes light, and instability becomes theater. Some white dwarfs steal enough matter to detonate completely. A white dwarf is usually the cooling remnant of an ordinary star, stable in its compact form and destined for a long fade into darkness. Yet under the right conditions, it can be pushed toward catastrophe. If a nearby companion feeds it enough matter, the white dwarf's mass can creep upward toward a critical limit. At that point, the pressure and temperature deep inside can trigger runaway carbon fusion. Because the star is supported by quantum pressure rather than ordinary expansion, it cannot regulate the reaction in the usual way. The result is sudden and devastating. The entire object can be torn apart in a thermonuclear supernova, leaving no white dwarf behind at all. For a brief time, it may outshine a whole galaxy. These explosions matter enormously because they seed space with heavy elements and also serve as distance markers across the cosmos. A seemingly quiet stellar ember, given too much from a neighbor, can become one of the brightest deaths in nature. Recurrent nova erupt again and again, instead of only once. Most of the time, when people imagine a stellar outburst, they picture a single dramatic event. Recurrent nova refuse to stay that simple. In these binary systems, a white dwarf keeps drawing hydrogen-rich gas from a companion. The material builds up on the surface until pressure and heat ignite it in a runaway thermonuclear flash. The blast throws matter outward and makes the system brighten dramatically, but crucially, the white dwarf survives. Then the process begins again. The cycle can repeat over years, decades, or longer depending on how quickly the fuel returns. That repetition gives these stars a special fascination. They are not one-time accidents. They are systems locked into an unstable rhythm of accumulation and release. Each eruption is both an ending and a promise of another. Watching one is like seeing a fuse relit in slow motion. The star is not destroyed. It is reset, poised to flare again when its borrowed surface becomes too crowded with fuel. Symbiotic stars pair a compact remnant with a swollen giant. Some binary systems are dramatic because both members are so different that they seem to belong to different eras of a stellar story. In a symbiotic star, one partner is often a white dwarf, while the other is a red giant, bloated enough to lose material into space through a steady wind. The compact star captures some of that drifting gas and heats it, creating a system that can glow across many wavelengths at once. The giant contributes a cool, expanded atmosphere. The remnant contributes fierce energy and sometimes eruptions. Between them sits a shared environment of ionized gas, slow wind, and unstable transfer. That mixture gives the system its name, though the relationship is not especially kind. It is more like uneasy dependence. From Earth, these objects can look richly complicated, with spectra that show both cool stellar features and high energy emission together. A symbiotic star is beautiful because it combines old age, death, feeding, and radiation into a single tangled household. X-ray binaries shine brightest in light our eyes can never see. Some of the most powerful stellar systems would look disappointingly ordinary if we relied only on human vision. Their real brilliance lies in X-rays, a form of light far too energetic for our eyes to detect. In an X-ray binary, a neutron star or black hole pulls gas from a companion. As that matter spirals inward, it is heated to extraordinary temperatures in the accretion flow, hot enough to glow in X-rays rather than visible light. That means the system's most dramatic story is hidden, unless we bring the right instruments. Once we do, an entirely different universe appears. The compact object reveals itself not by surface glow, but by the fury of falling matter. Some of these binaries flicker, pulse, or erupt. Others remain persistent beacons. What makes them so memorable is the contrast between appearance and reality. A star that seems unremarkable in the night sky may, in the unseen X-ray universe, be one of the most violent and luminous systems in its region. Some stars are known mainly by the wreckage they leave behind. There are times when the star itself is gone or nearly invisible, yet its aftermath still dominates the sky. Supernova remnants are the great examples. An exploded star can leave behind expanding filaments, glowing shells, and tangled clouds of shocked gas that remain visible for thousands of years. In some cases, a neutron star or pulsar survives at the center. In others, the remnant itself is the main clue that something extraordinary once happened there. The Crad Nebula is a famous case, still expanding from a supernova recorded by human observers nearly 1,000 years ago. The star's death threw matter into space and left behind a scene so vivid that the aftermath became more famous than the original star ever was. These remnants matter because they preserve motion, chemistry, and energy from the explosion. They are cosmic crime scenes that remain open for ages. Astronomers read them like detectives, using the debris to reconstruct a vanished stellar life. Others are famous because they should not exist at all. Astronomy has a way of becoming most interesting when the universe ignores the neat categories we invented. Some stars stand out not because they are especially bright or violent, but because their very existence seems to violate the expected rules. Certain blue stragglers look too young for their environment. Some helium-rich stars appear stripped in ways that challenge simple, single-star evolution. Merger products can carry properties that no ordinary birth would easily explain. Even certain stars in close binary systems seem to occupy brief, improbable phases that theory once treated as nearly impossible to catch. These objects are thrilling because they force astronomers to think like investigators rather than librarians. The sky is not just a list of types. It is a place where collisions, theft, mass transfer, failed assumptions, and hidden companions keep producing exceptions. A star that should not exist is often more valuable than 100 that behave properly, because it points straight toward physics we have not fully understood yet. Rare stars often appear where stellar life has gone badly sideways. If you looked for the simplest stellar lives, you would study stars evolving alone, burning fuel in fairly predictable stages, and ending according to their mass. Rare stars often come from situations where that neat script breaks apart. A companion star interferes. Mass is stolen. A merger changes the whole future. Rotation becomes extreme. Instability grows. A collapse leaves behind something compact and strange. In other words, the rarest objects often form not when stellar evolution proceeds smoothly, but when something disturbs it. That is why these stars are so revealing. They show what happens when gravity, crowding, timing, and chance push a system off its expected path. The result may be a pulsar with a doomed companion, a stripped core shining too hot, or an eruptive giant on the brink of disaster. Rare stars are not just unusual decorations in the sky. They are what stellar life looks like when the ordinary plan breaks and physics starts improvising. Population 3 stars, if found, would be relics from cosmic dawn. These are the legendary missing elders of astronomy, the first generation of stars thought to have formed after the universe cooled enough for gravity to gather pristine gas. At that time, there were almost no heavy elements, only the simplest ingredients left from the Big Bang, mostly hydrogen and helium. That matters because later generations of stars inherit carbon, oxygen, iron, and other elements from earlier stellar deaths. Population 3 stars had none of that. They would have been born in a cosmos still chemically young, making them fundamentally different from the stars we know. Many models suggest they were extremely massive and short-lived, blazing brightly before exploding and enriching the universe for everything that followed. If one were found directly, it would be like opening a window onto the first great chapter of starlight. These stars are fascinating not because we know them well, but because they stand at the threshold between a dark universe and a luminous one. No one has yet confirmed the universe's very first stars. Astronomers are confident that the earliest stars must have existed, because later cosmic history depends on them. Yet those first stars remain among the most elusive objects in all of science. The problem is partly distance and partly time. They formed in the young universe, far away and long ago, and likely lived brief, intense lives before exploding or collapsing. That means even the most powerful telescopes face a difficult task. The first stars may be too faint individually, too short-lived, or too blended into early galaxies to isolate with certainty. Instead, astronomers search for indirect traces, unusual chemical patterns in ancient stars, signatures in early galaxies, or hints in the radiation of the distant universe. What makes this so compelling is the scale of the mystery. We can map planets, image black hole shadows, and time pulsars with astonishing precision. Yet the very first stars that ended the cosmic dark ages still remain unconfirmed, just beyond the edge of directed diol. Discovery. Hypervelocity stars are racing so fast they can escape the galaxy. Most stars remain bound to the Milky Way, moving in orbits shaped by the galaxy's total gravity. Hypervelocity stars are different. They travel so fast that they can break free entirely and head outward into intergalactic space. That alone would be enough to make them extraordinary, but their origin makes them even better. The leading explanation involves the supermassive black hole at the center of our galaxy. If a binary star strays too close, the pair can be torn apart. One star may be captured while the other is flung away at tremendous speed, like a stone from a cosmic sling. The result is a stellar exile launched on a one-way trip out of the Milky Way. These stars are beautiful because they turn gravity into drama on the grandest scale. A quiet sun-like object can become a runaway, not through its own behavior, but because it wandered too near one of the most dangerous places in the galaxy. Some runaway stars may have been slingshotted by black holes. The idea sounds almost mythical. A star ventures too close to a black hole, and gravity hurls it away at astonishing speed. Yet, this is a serious astrophysical mechanism, and it may explain some of the fastest runaway stars ever seen. The process often begins with a binary pair approaching the supermassive black hole in the Milky Way's center. The black hole's gravity disrupts the pair. One star may be captured into a tight orbit around the black hole, while the other receives the leftover energy and is launched outward at enormous velocity. In that instant, an ordinary star becomes a projectile fired across the galaxy. This matters because it lets astronomers use those stars as traces of past interactions with the galactic center. A runaway star is not just lost. It carries a record of violence in its motion. Every one of them may be a survivor of an encounter where gravity behaved less like a pull and more like an explosion. Others were hurled away when their partners exploded beside them. Not every runaway star needs a black hole to explain its speed. Sometimes the cause is more intimate and more sudden. In a binary system, two stars orbit a common center, each bound to the other's gravity. If one of them explodes as a supernova, that balance can be shattered in an instant. The system loses mass, receives an asymmetric kick, or both. The surviving companion, no longer anchored by the old orbit, can be flung outward through space at high speed. What was once an ordinary member of a pair becomes a solitary traveler carrying the memory of a catastrophe. This mechanism is especially striking because it turns companionship into launch force. The star's speed is not self-made. It is inherited from an orbit that was violently broken. In some cases, astronomers can even trace the motion of a runaway star back toward a remnant or a star-forming region, reconstructing the moment its partner died and sent it hurtling away. Blue lurkers hide in clusters as stars that look quietly suspicious. These are subtler relatives of blue stragglers, stars in old clusters that do not stand out dramatically at first glance, yet still appear younger or more massive than they should. They are called blue lurkers because they hover near the expected stellar sequence while carrying hints that something unusual has happened. Perhaps they gained mass from a companion without becoming as obviously bright and blue as a classic straggler. Perhaps they merged in the way that left only a muted signature. Whatever the path, the result is a star that blends in just enough to be overlooked. That makes them fascinating because they suggest stellar reinvention may be more common than we once realized. Not every odd history announces itself loudly. Some stars hide their past in modest color shifts, subtle mass excesses, or suspicious rotation. A blue lurker is a reminder that in crowded clusters, the most intriguing imposters are not always the flashy ones. Some are hiding in plain sight. Subdwarf stars are tiny, hot survivors stripped by close companions. These stars are hotter than many ordinary stars, yet much smaller and less luminous than a normal giant would be at the same temperature. That odd combination comes from a violent loss of outer layers. A close companion can strip away most of a red giant's hydrogen envelope before the star finishes its usual evolution. leaving behind a compact core still burning helium. The result is a hot subdwarf, a stellar survivor caught in a stage that is both exposed and abbreviated. They often appear in binary systems because companionship is the most efficient sculptor of this outcome, though mergers may also create some examples. What makes them so compelling is how much they compress into one object. You have the heat of a deeper layer, the size of something much smaller, and the biography of a star whose future was rewritten by proximity. A hot subdwarf is not simply a faint blue point. It is a stripped life still burning, against expectation. Extreme helium stars are rare suns with almost no hydrogen left. Hydrogen usually defines a star. It is the main fuel, the dominant outer ingredient, and the great common thread linking the vast majority of stellar lives. So, when astronomers find a star whose atmosphere is overwhelmingly helium instead, it immediately feels wrong in the most exciting way. Extreme helium stars are rare, luminous objects that appear to have lost almost all trace of normal hydrogen-rich outer layers. Some may have formed when two white dwarfs merged. Others may reflect a late, violent rearrangement in stellar evolution. However they arise, the result is extraordinary. We are looking at a star whose surface chemistry seems almost inside out compared with the ordinary rulebook. Their spectra reveal this clearly, turning them into clues about unusual pathways that most stars never follow. They matter because they expose how flexible stellar endings can be. Even the most basic expectation about what a star should be made of can fail, and when it does, the sky becomes much more interesting. Some stars pulsate because their outer layers trap and release heat. One of the most elegant reasons a star can vary in brightness comes from a kind of stellar heat valve hidden in its outer layers. In certain zones, gas can become more opaque as it is compressed. That means heat gets trapped for a while instead of escaping easily. Pressure builds, the layer expands, the gas becomes more transparent, and the trapped energy finally leaks out. Then the layer cools and contracts, setting up the cycle again. This repeating process drives pulsations in several important types of variable stars. The star brightens and dims not because something blocks our view, but because its own outer layers are breathing in response to trapped heat and released pressure. It is a beautiful example of physics becoming rhythm. What appears to the eye as a change in brightness is actually a mechanical and thermal conversation happening in the star's envelope. A pulsating star is not flickering randomly. It is keeping time with its own structure. Others tremble with starquakes that reveal their hidden interiors. Just as earthquakes reveal the layered structure of Earth, starquakes allow astronomers to probe the inside of stars by studying tiny oscillations on their surfaces. These vibrations may be driven by pressure waves, gravity waves, rotation, or internal structure, and they leave subtle fingerprints in the light. By measuring those patterns carefully, astronomers can infer a star's mass, age, density profile, and even details about its core. This field, called asteroseismology, turns brightness changes into a kind of diagnostic music. The star does not need to erupt or explode to become revealing. A faint tremble is enough. That makes these objects especially captivating because the drama is hidden in delicacy rather than violence. A star can be telling us about its deepest layers through motion so slight that only precise instruments can catch them. When that signal is decoded, we are no longer just looking at a shining surface. We are listening to the architecture of a star from the inside out. Asteroseismology lets astronomers listen to stars instead of only seeing them. A star can look calm from a distance and still be ringing with hidden motion. Tiny waves move through its interior, rise to the surface, and cause slight changes in brightness or motion that sensitive telescopes can measure. Astronomers study those patterns much the way a musician might study the tone of an instrument. A large hollow object sounds different from a dense compact one, and a star follows the same principle. Its oscillations carry information about age, internal layering, rotation, and the size of the core. This is why asteroseismology feels so magical. It turns starlight into structure. Instead of guessing what lies beneath the surface, scientists can infer it from the star's own vibrations. The method has transformed ordinary points of light into objects with readable interiors. A star no longer needs to explode to reveal itself. Sometimes all it has to do is tremble, and the universe suddenly becomes far less silent. White dwarfs can crystallize as they cool, becoming cosmic solids. After a white dwarf has spent ages radiating away its heat, something extraordinary can begin to happen deep inside it. The ions in its dense interior slow down enough to arrange themselves into an ordered lattice, rather than remaining in a hot, fluid state. In other words, the heart of the dead star begins to crystallize. This is not crystal in the everyday sense of a clear gemstone catching sunlight. It is matter under immense density, packed into a rigid structure inside an Earth-sized remnant. The process happens gradually over billions of years, and it changes how the star cools. Heat is released as the interior freezes, which means the star lingers warmer than it otherwise would. That gives astronomers a way to study the phenomenon by comparing real white dwarfs to cooling models. A stellar ember can spend unthinkable ages transforming into a giant solid sphere, and that is one of the strangest endings an ordinary star can have. Some dead stars may contain cores of slowly forming crystal. The remarkable thing about this transformation is that it may begin at the center and grow outward in stages, making the interior of a white dwarf less like a dying gas sphere and more like an object with an enlarging crystalline heart. At first, the star still looks much the same from the outside, just faint and compact. But deep within, the matter is rearranging itself into a more ordered state under crushing density. This means a white dwarf can carry a hidden history of gradual freezing, with the oldest parts of its interior becoming rigid first. The idea is astonishing because it gives a dead star an internal evolution long after nuclear burning has ended. Even after the dramatic life of the star is over, the story continues in silence. Its core does not simply cool. It slowly changes phase, turning the remnant into a kind of immense celestial relic, still evolving in darkness long after its bright days have passed. Crystallizing white dwarfs cool more slowly than expected. If a white dwarf simply lost heat without any surprises, astronomers could use its temperature as a fairly direct clock. But crystallization complicates that clock in a beautiful way. As the interior freezes, latent heat is released, much as water gives off energy when it becomes ice. In a white dwarf, the conditions are vastly more extreme, yet the principle is similar. That extra heat slows the fading process, keeping the star brighter for longer than simple cooling models would predict. For astronomers, this matters a great deal. White dwarfs are used to estimate the ages of star clusters and populations, so anything that changes their cooling rate changes the inferred timeline. The effect was not just a theoretical curiosity. It showed up in real observations, where groups of white dwarfs piled up at certain brightnesses in a way that hinted at a delayed fade. Even in death, these stars can cheat the clock a little by freezing. Carbon-oxygen white dwarfs are stellar embers made of fused ash. When a sun-like star reaches the end of its normal life, it does not leave behind hydrogen as its final signature. By then, the inner story has moved much deeper. Over time, Helium fusion in the interior has built up carbon and oxygen, and when the outer layers are shed, those products remain as the compact remnant. That means many white dwarfs are essentially made of the ash from earlier nuclear burning. The phrase sounds poetic, but it is also exact in a physical sense. These are the leftovers from a long internal furnace, compressed into an object no larger than a planet. Their surfaces may wear thin atmospheres of hydrogen or helium, yet the deeper body is mostly carbon and oxygen packed at extraordinary density. A star that once shone by fusion ends as a hidden archive of what it forged. In that tiny remnant lies the record of the stellar fire that came before, preserved as an ember of transformed matter. Oxygen neon white dwarfs come from heavier stars with stranger endings. Not all white dwarfs share the same internal recipe. Stars a little heavier than the Sun can drive fusion further before their lives end, building cores rich in oxygen and neon rather than mostly carbon and oxygen. These remnants are rarer and especially interesting because they sit closer to the boundary between quiet stellar death and more violent outcomes. Their parent stars were hefty enough to push deeper into nuclear burning, but not always enough to trigger a classic core collapse supernova. The result is a remnant that tells a more complicated story, one balanced on the edge between two stellar fates. For astronomers, that makes these white dwarfs valuable clues to the fine divisions in stellar evolution. A modest change in birth mass can decide whether a star leaves behind a dense oxygen neon core or dies much more dramatically. These remnants are reminders that stellar endings are not arranged in broad, simple bins. Sometimes the most revealing cases live near the thresholds. Some stellar corpses are so faint they take billions of years. White dwarfs are patient objects. Once the nuclear engine is gone, they do not burn their way onward into a new bright phase. They simply radiate stored heat and cool, slowly and relentlessly, over immense stretches of cosmic time. That process is so gradual that the universe is not yet old enough for any white dwarf to have fully faded into a cold black dwarf. In that sense, every white dwarf ever formed is still partway through its long descent. These remnants begin intensely hot, then dim over billions of years until they become faint and difficult to detect. What makes this so fascinating is the scale of the timeline. Entire continents can rise and vanish on Earth in the time it takes one of these objects to cool significantly. Civilizations are less than a blink. Even galaxies evolve while a white dwarf is still shedding the last memory of its heat. Death, for some stars, is not a single event, but a nearly endless twilight. A white dwarf can be Earth-sized, yet Sun-like in mass. That contrast is one of the great shocks of astronomy. A white dwarf can be packed into a volume comparable to Earth, while holding a mass similar to that of the Sun. The result is density far beyond ordinary experience. A spoonful of its material would weigh enormously on Earth, though not as extravagantly as neutron star matter. The reason such an object can exist is quantum mechanics. The electrons in the star's interior resist being pushed into the same states, and that resistance provides the pressure that supports the remnant against further collapse. What makes this beautiful is how different a star becomes without ceasing to be a star's remains. It is no longer a broad, glowing sphere with fusion at its core. It is a compact object where the rules of the microscopic world hold up something astronomical in scale. A white dwarf shows that a star's final dignity can come not from fire, but from quantum resistance written across a planet-sized corpse. Neutron stars can have mountains smaller than grains on a globe. On Earth, a mountain is something vast, towering, and easy to picture. On a neutron star, the same word becomes almost absurd. The gravity at the surface is so intense that matter is squeezed brutally flat. The crust can support only the tiniest deformations before the immense pull overwhelms them. That means a feature that counts as a mountain on a neutron star may be no taller than a fraction of a millimeter in human terms. Scaled to the size of the whole object, it is almost nothing, like a tiny roughness on a polished sphere. And yet that tiny bump matters. Because the star can spin rapidly, even a minuscule asymmetry can influence the way it moves and radiates. This is one of the strangest lessons rare stars teach. Physical language still applies, but the meanings are transformed by extremity. A mountain can become microscopic and still count as one of the most consequential landforms in the universe. Even those tiny mountains can shake space with gravitational waves. If a neutron star were perfectly symmetrical, its rapid rotation would be elegant but quieter in a certain sense. Add even a tiny persistent bump, and the story changes. As the star spins, that unevenness means the mass is not distributed with perfect balance, and according to general relativity, an accelerating asymmetry can radiate gravitational waves. These are ripples in space-time itself, faint and difficult to detect, but real. The astonishing part is the scale mismatch. A distortion tiny by everyday standards, carried on an object as dense and fast as a neutron star, may be enough to send those ripples outward across the cosmos. Scientists search for such continuous signals because they would reveal not a violent collision, but an ongoing imperfection turning steadily in space. That is such a haunting image. A dead star, nearly perfect, yet not quite. And because of that tiny flaw, the fabric of the universe shivers in rhythm with its spin, broadcasting structure through gravity alone. Magnetars can unleash giant flares strong enough to affect Earth's atmosphere. When a magnetar suffers a sudden rearrangement in its magnetic field or crust, it can release an enormous burst of high-energy radiation called a giant flare. These are among the most violent flashes known from any star-sized object. One famous event in 2004 was so powerful that it briefly disturbed Earth's upper atmosphere, even though the source lay tens of thousands of light-years away. That is a stunning sentence to have to believe. A dead star in another part of the galaxy released enough energy in a moment to leave a measurable fingerprint here. The flare itself likely came from a catastrophic magnetic adjustment, a kind of stellar convulsion in an object already living under impossible tension. For a fraction of a second, the magnetar became one of the brightest high-energy sources in the sky. It is a reminder that distance does not always mean safety from influence. In astronomy, even a remote corpse can still reach us. Their magnetic fields could erase every credit card from half the moon. This comparison is dramatic, but it captures the outrageous scale of a magnetar's field better than abstract numbers ever could. If one of these objects were placed halfway to the moon, its magnetic influence would be strong enough to destroy magnetic strips on everyday cards across a vast region. That thought experiment is useful because magnetar fields are otherwise almost impossible to picture. They are not just stronger than anything humans normally encounter. They are so extreme that they can distort atoms, influence light, and dominate the surrounding physics in ways that seem almost unfair. The star itself is only about the size of a city, yet the field around it behaves like an invisible tyrant. What is most fascinating is that this is not the field of a living giant star. It belongs to a remnant, something formed after collapse, compressed into a state where magnetism becomes almost as important as gravity. A magnetar turns invisible force into one of the cosmos's fiercest realities. Some magnetars also behave like radio pulsars, blurring old categories. Astronomy loves tidy labels until the universe starts ignoring them. For a time, Magnetars and radio pulsars seemed like separate classes. One group was defined by extreme magnetic activity and high-energy outbursts. The other was known for regular beams of radio emission from spinning neutron stars. Then observations revealed objects that did both. Some magnetars were caught producing radio pulses, while certain pulsars showed hints of magnetar-like behavior. Suddenly, the boundaries looked less like walls and more like regions in a larger landscape of neutron star possibilities. That shift matters because it reminds us that nature does not always build discrete boxes. A neutron star can move through different behaviors as its field, rotation, and environment evolve. What once looked like separate species may be related expressions of the same deep physics. This is one reason rare stars are so valuable. They expose where classification starts to wobble and where the real universe turns out to be more continuous and inventive than our names. A dead star's magnetic fury can outshine whole galaxies for moments. During the opening instant of a giant magnetar flare, the energy released can be so intense that for a heartbeat of cosmic time, the source rivals or exceeds the brightness of an entire galaxy at certain wavelengths. That idea feels unreasonable until you remember what is being tapped. A magnetar stores a colossal amount of energy in its twisted magnetic field, and when part of that field suddenly reconfigures, the result is not a polite flash. It is an eruption from one of the most extreme environments in nature. The initial spike can be blinding to instruments, followed by a fading tail shaped by the star's rotation. This is especially astonishing because the object responsible is so small. You are not looking at a great cloud, or a galaxy, or a sprawling stellar nursery. You are looking at something city-sized, a compact remnant, briefly dominating the high-energy sky through the violence of pure magnetism. Few astronomical contrasts are more thrilling than that. Soft gamma repeaters were once mysterious signals before magnetars explained them. When astronomers first detected bursts of gamma rays that repeated from the same sources, the phenomenon did not fit the usual categories. The bursts were too soft in energy to match some of the better-known gamma ray events, yet too intense and strange to ignore. Because they repeated, they also could not be one-time cataclysms like certain stellar explosions. For a while, they were simply mysterious. Then the magnetar picture brought coherence to the puzzle. A neutron star with an immense magnetic field could crack its crust, twist its magnetosphere, and produce exactly the sort of repeated high-energy flashes being observed. Suddenly, these odd signals became part of a larger story about magnetic stress and stellar remnants living under extreme conditions. This is one of the pleasures of astronomy. A baffling phenomenon can sit in the sky for years as a loose thread. Then a new physical idea arrives and pulls the whole pattern into view, turning mystery into an even deeper kind of wonder. Anomalous X-ray pulsars turned out to be magnetic monsters too. These objects got their awkward name because they behaved like X-ray pulsars, yet did not seem to have the usual power source. In ordinary accreting systems, X-rays come from matter, falling onto a compact star. But anomalous X-ray pulsars shone persistently in X-rays without obvious signs of a feeding companion. Their energy budget did not add up under the old assumptions. The eventual answer was that they were not ordinary pulsars at all, but likely magnetars or close relatives. Their luminosity came not from stolen matter, but from the decay and rearrangement of enormous magnetic fields. That recognition linked them to soft gamma repeaters and helped reveal an entire family of neutron stars powered in unusual ways. It is a superb example of how rare stars unsettle theory. The universe presented a class of objects that looked familiar at first, then turned out to be something far stranger. Their anomaly was not a nuisance. It was the clue. Some neutron stars may have quark-rich matter in their cores. Push matter to sufficient density and ordinary nuclear structure may no longer be the end of the story. In the deepest interiors of neutron stars, where pressure exceeds anything accessible on Earth, some physicists think matter may enter unfamiliar states. One possibility is that neutrons break down into their constituent quarks, creating a core of quark-rich matter, or something even more exotic. This remains uncertain, but the idea is not fantasy. It arises from serious attempts to understand how matter behaves when crushed beyond ordinary atomic and nuclear limits. What makes it so fascinating is that neutron stars may contain forms of substance we cannot manufacture and barely know how to describe. A city-sized stellar corpse could hold a core unlike anything in the familiar universe around us. Astronomers test these ideas indirectly through mass measurements, radii, spin, and signals from neutron star collisions. The object becomes a riddle box where gravity compresses physics into states that theory can only partially anticipate. Astronomers still do not know exactly what neutron stars contain. That uncertainty is one of the most exciting facts about them. We can measure their mass. We can estimate their size. We can observe their pulses, flares, mergers, and gravitational effects. Yet the exact composition of their interiors remains one of modern astrophysics' great open questions. Are they mostly tightly packed neutrons all the way down? Do their cores contain hyperons, free quarks, or superfluid mixtures unlike anything we encounter elsewhere? Does the internal structure change dramatically with depth? These are not small details. They determine how the star responds to pressure, how large it can be before collapsing further, and how it behaves when perturbed. Every new observation helps narrow the possibilities, but the full answer is still hidden behind distance and density. This is a wonderful kind of ignorance. We are not guessing whether neutron stars exist. We are staring directly at them and still asking what matter becomes under their conditions. Rare stars preserve mysteries at the center of certainty. Rare stars often matter most because they test impossible physics. An ordinary laboratory is limited by budget, safety, engineering, and the laws of matter under human-scale conditions. Rare stars ignore those limits completely. They create densities, temperatures, magnetic fields, and gravitational regimes that no machine on Earth can sustain. That makes them more than curiosities. They become experiments already running in the universe, waiting for us to interpret the results. White dwarfs test quantum pressure. Neutron stars probe ultra-dense matter. Magnetars confront us with impossible magnetism. Pulsars let us test timing and relativity with extraordinary precision. The point is not just that these stars are weird. It is that they carry physics into places where equations are no longer comfortable, and then they send signals back across space. When astronomers study them, they are not only cataloging odd objects, they are asking nature how matter, light, gravity, and time behave under extremes no earthly apparatus can match. Rare stars are where theory goes to be challenged. They turn the night sky into a laboratory beyond Earth. Once you begin to understand what rare stars are doing, the sky stops feeling like scenery and starts feeling like active research space. There are quantum mechanical remnants cooling into crystal, neutron stars pulsing with precise clocks, magnetars storing violence in invisible fields, and binary systems where matter streams, crashes, ignites, and reshapes futures. None of it is staged for us, yet all of it can be measured if we know how to read the signals. Telescopes become instruments not just of sight, but of experiment. A flash, a wobble, a spectrum, or a delay in a pulse can tell us how matter behaves when compressed beyond imagination, or how gravity moves through a region of intense curvature. That is why rare stars are so intoxicating. they make the universe feel both enormous and intimate. The most distant and extreme objects become partners in discovery. The sky above us is not passive. It is full of ongoing tests, and some of the most important are written in strange starlight. Wolf-Rayet stars can sculpt enormous bubbles in surrounding gas. A Wolf-Rayet star does not simply shine into space. It attacks space. Its wind rushes outward at astonishing speed, slamming into the surrounding gas and sweeping it into vast shells and cavities. Over time, that pressure can hollow out enormous bubbles in the interstellar medium, like a storm carving an empty chamber in a cloud. These structures can stretch across many light years, glowing where shock waves heat the gas and trigger new patterns of light. What makes this so captivating is the scale of influence. One star can alter an entire region around it, not by exploding, but by living violently enough. The star becomes an architect of emptiness, pushing matter aside and tracing its presence in enormous curved walls. When astronomers image these bubbles, they are not just looking at scenery. They are seeing the reach of a rare star made visible, a portrait painted not by light alone, but by wind, pressure, and relentless stellar force. Some are wrapped in pinwheel dust spirals made by binary winds. In a few rare binary systems, two fierce stellar winds collide and create something almost too graceful for such violent origins. One star may be a Wolf-Rayet object rich in carbon, while the companion drives a powerful wind of its own. Where those winds crash together, the gas can cool enough for dust to form. Then, the orbital motion of the pair winds that fresh dust outward into a spiral. The result is a glowing pinwheel pattern turning through space, delicate in appearance, and born from collision. It is one of the loveliest tricks in stellar astronomy. Instead of chaos looking chaotic, it becomes ordered by motion. Every turn of the orbit writes another loop into the spiral, and the structure expands as a record of time itself. A telescope can catch this geometry frozen in light, showing that even some of the harshest stars can produce shapes of eerie elegance when companionship and wind conspire just right. APEP is a rare stellar system drawing spirals across space. APEP is one of the most arresting named systems in the sky, not because it is close or familiar, but because it seems to sketch a giant dusty whirlpool around itself. At its heart lies a rare and massive stellar arrangement involving a Wolf-Rayet star and powerful outflowing winds. Infrared observations revealed a remarkable spiral plume of dust streaming away from the system, a giant pattern built through motion and collision. What makes APEP especially intriguing is that the dust appears to expand more slowly than the underlying wind speed would suggest, hinting at a more complicated geometry, perhaps shaped by direction, rotation, or hidden structure in the outflow. It feels less like a static object and more like an active machine drawing a pattern into the dark. Even the name adds drama. APEP was the serpent of chaos in Egyptian mythology, and the system lives up to it, part beauty, part violence, part mystery still being untangled. WR124 is a doomed giant blowing off its future shroud. This star is a spectacular example of a massive object already preparing the scene for its own end. WR124 sits inside a glowing nebula of material that it expelled through fierce stellar winds, building a cocoon around itself while it still lives. The surrounding cloud, known as M1-67, looks almost like a future ghost waiting in advance. The star at the center is unstable, hot, and short-lived on cosmic timescales. It is the kind of object astronomers study because it shows a massive star in a late and revealing phase, stripped enough to expose deeper layers and violent enough to hurl matter far into space. What you see is not merely a star and not merely a nebula. It is a relationship between the two, the central engine and the future shroud it has made from its own body. Few sights capture impending stellar ruin with such grandeur. Some Wolf-Rayet stars may be moments away from supernova on cosmic timescales. In human terms, these stars are ancient and impossibly distant. In cosmic terms, some may be standing almost at the edge of the trapdoor. A Wolf-Rayet star has already burned through enormous amounts of fuel and shed much of its outer mass, revealing layers that belong to a late chapter of stellar evolution. That means when astronomers observe one, they may be seeing an object that has only a tiny fraction of its lifespan left. Tiny, in this case, may still mean thousands or hundreds of thousands of years, which is long to us, but a final breath to a massive star. This is what gives them such tension. They are not merely unusual stars. They are candidates for catastrophe already underway. Every fierce wind and exposed layer hints that the core is racing through its remaining options. One day, the balance will fail, and the star may disappear in a blast that had been silently approaching the whole time. Their winds are so fierce they can reshape nearby nebulae. Nebulae are often imagined as passive clouds, luminous backdrops waiting to be photographed. Around rare, massive stars, that calm picture breaks down. The outflow from a Wolf-Rayet star can be so fast and energetic that it pushes, compresses, and distorts nearby gas, changing the shape of an entire nebula environment. Filaments are bent. Shells are brightened. Older material from earlier evolutionary stages may be swept up and rearranged into arcs or clumps. In some cases, the wind from the star plows into matter it expelled during a previous red supergiant phase, creating intricate layers of interaction. That history becomes visible in the structure of the nebula itself. You are not just seeing a cloud. You are seeing a conversation between past and present versions of the same star. The force of that idea is wonderful. A star can rewrite the space around it multiple times, leaving visible evidence that stellar evolution is not only internal. It sculpts its surroundings too. These stars expose fusion layers ordinary stars keep hidden inside. Most stars guard their internal chemistry beneath thick outer envelopes, so we see only the surface, not the deeper layers where the real transformation happens. Wolf-Rayet stars break that rule. Their ferocious mass loss strips away the usual covering and exposes regions enriched by advanced fusion. That means astronomers can detect unusual surface abundances of elements like helium, nitrogen, carbon, or oxygen, depending on which layer has been uncovered. In effect, the star has turned part of its interior outward. This is thrilling because it lets us study a stage of stellar processing that is normally buried and inaccessible. The star becomes a living cutaway diagram of itself. What would usually remain theoretical now speaks through the spectrum. It is one thing to know that fusion builds new elements in deep stellar furnaces. It is another to see a star whose violent history has peeled back the surface and made those inner chapters directly visible. It feels like catching a hidden machine without its casing. In rare cases, they seem almost more like stellar skeletons. There are moments in astronomy when metaphor feels unusually close to the truth. Some highly stripped stars have lost so much of their outer mass that what remains looks almost like the bare framework of a once much larger object. The comparison to a skeleton works because we are seeing an exposed remnant of structure, not the fuller form the star once had. The star is still alive in the technical sense, still burning and radiating, yet it has been pared down to something stark and revealing. Its spectrum tells the story of layers uncovered. Its wind speaks of continuing loss. Its brilliance comes not from abundance, but from exposure and extremity. These objects are haunting because they show survival in a reduced form. A massive star does not always die all at once. Sometimes it is stripped until its deeper architecture stands nearly bare, glowing fiercely while looking less like a complete sun and more like the radiant bones of one. A massive star can become stranger the more of itself it loses. Usually we imagine loss as simplification. In stellar evolution, loss can create the opposite. A massive star that sheds its outer layers may reveal behaviors, chemistry, and structures far more exotic than it showed in its fuller youth. While it was wrapped in hydrogen, it might have looked relatively ordinary for a giant star. Strip that envelope away through winds or binary interaction, and suddenly deeper fusion products appear. New instabilities emerge, and the star enters categories that feel increasingly bizarre. The object becomes hotter, more compact in some ways, and more informative to astronomers, all because it has less of itself left. That reversal is one of the most beautiful patterns in rare star astronomy. The closer such a star comes to destruction, the more revealing it becomes. Layers vanish, secrets emerge. What once looked like an ordinary brilliant star becomes a physics lesson in exposed form. In the universe, losing substance can sometimes mean gaining identity. The brightest rare stars are often already on the edge of ruin. There is something almost tragic about the most luminous rare stars. Their brilliance can feel like triumph, yet in many cases it signals instability, excess, and an approach to disaster. Extremely massive stars burn through fuel with astonishing speed. Their radiation presses hard on their own outer layers. Their winds intensify. Eruptions become possible. Instead of glowing calmly for billions of years, they live in a state of dangerous abundance, spending themselves with spectacular impatience. That is why some of the brightest rare stars are not examples of comfortable success. They are examples of a system under strain. The light we admire is often tied to a life being consumed at a tremendous rate. A luminous blue variable or Wolf-Rayet star can dominate its region and still be nearing the end of the road. The sky sometimes makes ruin look magnificent. A star can dazzle most when its balance is failing, turning brilliance into a warning written in light. Blue stragglers may form when stars collide in crowded clusters. In the packed interiors of ancient star clusters, gravity can bring stars into surprisingly intimate encounters. The odds of a direct collision are still small in absolute terms, but in those crowded environments they become possible enough to matter. When two stars merge, the result can be a single rejuvenated object with more mass and fresh hydrogen available for burning. That new star shines hotter and bluer than the older cluster population around it, standing out as a kind of youth fraud inside a stellar retirement home. This formation route is especially compelling because it turns crowding into creation. The cluster is not merely a collection of old stars aging together. It becomes a place where proximity can rewrite destiny. A collision is usually imagined as destruction. Yet here, it can produce a star that looks renewed. In a cluster where most bright stars should have faded long ago, a merger can create a fresh imposter and make the old population look suddenly less settled. They can also form when one star quietly drains another. Not every blue straggler needs a dramatic crash. Some may be built through a slower and more secretive kind of theft. In a binary system, one star can evolve and expand until its gas begins to flow toward the companion. If enough mass is transferred, the receiving star becomes heavier, hotter, and bluer than it would have been on its own. To an outside observer in the cluster, it can look oddly youthful compared with neighboring stars of the same age. This route is fascinating because it is less explosive and more intimate. The transformation happens through quiet imbalance, one star fading while the other is refreshed. In some cases, the donor is eventually reduced to a faint remnant, leaving the brightened star looking almost innocent unless astronomers search carefully for clues. These objects remind us that stellar deception is not always born from violence. Sometimes it comes from long partnership, unequal exchange, and a history hidden in borrowed mass. In either case, they look younger than their neighbors. That visual contradiction is what makes blue stragglers so memorable. Whether they formed through merger or mass transfer, the result is the same to a first approximation. The star ends up hotter and more luminous than it ought to be for the age of the cluster around it. In a population where the more massive stars should already have evolved away from the main sequence, these objects are still sitting there, blue and conspicuous, as though they somehow missed the memo about aging. That tension between appearance and history is irresistible. Astronomy often relies on reading age from where a star sits in a cluster diagram. Blue stragglers disrupt that confidence. They look like late arrivals in systems where all the stars should have formed together long ago. The eye wants to trust what it sees, but these stars teach caution. A bright blue surface can be a disguise. In stellar populations, youth can sometimes be a costume stitched from an older story. Rare stars can fool astronomers by wearing the wrong age. We like to think stars advertise their stage of life honestly through color, brightness, and temperature. Rare stars often undermine that assumption. A merger can create an apparently youthful object from old ingredients. Mass transfer can refresh a companion and make it look younger than the system it belongs to. A stripped star can appear unexpectedly hot because its deeper layers are exposed. In all these cases, the visible properties hint at one age or one pathway, while the true history lies elsewhere. That makes rare stars especially seductive and frustrating. They tempt us with surface clues, then punish us for trusting them too quickly. For astronomers, this is not merely a nuisance. It is an invitation to investigate more deeply through motion, chemistry, binarity, and theoretical modeling. The star becomes a false passport in the archive of the sky. It presents one identity and carries another. Rare stars remind us that age in astronomy is not always worn openly. Sometimes it is disguised. Some clusters preserve these imposter stars for billions of years. One reason blue stragglers have become such important clues is that star clusters act like natural archives. A globular cluster may be ancient beyond easy human comprehension, and within that old population, the imposter stars can remain visible long enough to be studied in detail. That persistence matters. It means the aftermath of merger or mass transfer is not always fleeting. A rejuvenated star can remain on display, shining in a way that keeps the evidence of past interactions alive across billions of years. The cluster becomes a museum of stellar misdirection, full of stars that mostly obey the expected age pattern, and a few that plainly do not. Because the rest of the cluster is so old and well-behaved, the imposters stand out more sharply. Their existence says that even in a system whose main story was written long ago, later drama can still leave enduring marks. Ancient clusters are not frozen histories. They preserve interruptions as well as order. A star's true story is not always written on its surface. That idea may be the central lesson of rare star astronomy. We see only the outer light, the spectrum, the brightness, the color, the pulse. From that, we try to reconstruct a hidden life. Sometimes the surface tells the truth plainly. Sometimes it conceals more than it reveals. A star may look youthful after a merger. It may look unusually hot because it was stripped. It may appear ordinary while hiding a strange companion whose influence changed everything. This is why astronomers rely on more than appearance. Motion, Orbital behavior, chemical composition, and population context all help uncover the deeper story. The star's visible face is only the beginning of the evidence. That is what makes these objects so rich. They turn astronomy into biography by inference. You never hold the object in your hands, yet you can still discover that its current state is the result of theft, collision, loss, or revival. The surface glows. The real story hides underneath. Some rare stars are detectives' work, not simple sightings. There are stars that announce themselves dramatically with eruptions or strange light curves. Others require something closer to forensic reconstruction. A suspicious color in an old cluster, a peculiar abundance pattern, a faint orbital wobble, or an unexpected temperature can all serve as clues that something unusual has happened. On their own, those details may not seem decisive. Together, they can reveal a merger, a stripped envelope, a hidden companion, or an evolutionary pathway that would otherwise remain invisible. This is why studying rare stars often feels less like cataloging and more like solving a layered case. The evidence arrives in fragments and rarely in perfect order. Astronomers compare models, examine spectra, search for periodic motion, and ask what sequence of events could produce the star now on display. That investigative quality is part of the fascination. Rare stars are not just beautiful objects. They are mysteries with physical evidence, and the solution often lies in learning how to read what starlight is quietly confessing. Their chemistry can reveal ancient theft, merger, or violent loss. A star's composition is not merely a list of elements. It can be a historical record. If deeper layers have been exposed, the surface may show products of fusion that do not belong in an untouched outer atmosphere. If a star has accreted matter from a companion, certain abundance anomalies may linger as evidence of that exchange. If two stars merged, the new object may carry a chemical pattern that does not fit ordinary single-star evolution. This is one of the great powers of stellar spectroscopy. The chemistry is not only what the star is made of now, it is a trace of what has happened to it. That makes rare stars deeply satisfying to study because they are readable in more than one sense. You can measure the light and infer a sequence of events. A violent loss, a quiet theft, or a buried merger may leave no visible scar in shape, yet the atoms remain talkative. They remember the history even when the surface tries to pass as innocent. Spectra let astronomers read what these odd stars are hiding. Spread a star's light into a rainbow, and it stops being just beautiful. It becomes legible. Dark absorption lines and bright emission features reveal which elements are present, how hot the gas is, whether material is flowing outward, and even whether unseen companions may be involved. For rare stars, this is often the decisive tool. A stripped star announces exposed helium through its lines. A wolf-reared star shows powerful emissions from its fierce wind. A chemically peculiar object betrays unusual abundances that hint at past mass transfer or internal mixing. A hidden binary can be uncovered through shifting spectral features as the stars orbit. This is why spectroscopy feels almost magical. A distant point of light turns into testimony. The star cannot be touched, yet its light carries structured information about temperature, motion, and history. In the case of rare stars, that information is often the difference between mystery and understanding. The oddities are real, but the spectrum tells us why. A weird star is often a normal star after something dramatic happened. That may be the most satisfying twist in all of this. Many rare stars are not separate creations born under entirely different rules. They are ordinary stars, altered by extraordinary events. A normal star that merged with another may become a blue straggler. A familiar giant stripped by a companion may become a helium-rich remnant. A standard stellar core left behind after collapse may turn into a pulsar, magnetar, or accreting compact object, depending on what happened next. The weirdness often lies not in the starting point, but in the history. Something dramatic interrupted the usual script, and the result now looks exotic. That is a wonderful thought, because it makes the universe feel more dynamic and less compartmentalized. Rare stars are not always a separate cast. They are often the recognizable cast after collision, theft, exposure, or catastrophe. In other words, the strangest stars in the sky may simply be the familiar ones after life went gloriously and catastrophically off course. Some red giants pulse so deeply their brightness rises like breathing. Near the end of a modest star's life, the outer layers can become so swollen and unstable that the whole star begins to expand and contract in slow, powerful cycles. The effect is not a tiny shimmer. It can be a broad, heaving change in size, temperature, and light, as though the star is breathing across space. These pulsations happen because gravity and pressure keep falling out of step with one another in the giant envelope. As the outer layers expand, they cool and dim. As they contract, they heat and brighten again. What makes this so spellbinding is the scale. We are not talking about weather on a star. We are talking about the entire visible body of the star moving inward and outward over weeks or months. A red giant in this state feels less like a fixed sun and more like a living rhythm. Even very old stars can still move with surprising grandeur before they finally fade. Nearer variables swell and fade in cycles that can last months. Some stars are patient performers. Mirror variables are old red giants whose brightness rises and falls over long, regular cycles, often lasting many months. At their brightest, they can become dramatically more visible, and at their faintest, they may almost disappear from ordinary view. The star mirror itself astonished early skywatchers because it seemed to vanish and return, earning a name that means wonderful. The reason for this strange behavior lies in powerful pulsation. The star's outer layers grow and shrink in a repeating cycle, changing both its size and temperature. Because these stars are so cool, even modest temperature shifts can have a huge effect on the visible light they emit. That is why the change can seem almost theatrical. A star is not switching on and off. It is slowly breathing and changing color in a way that transforms its apparent brightness. Mirror variables make the sky feel patient, rhythmic, and deeply alive. RV Tauri stars dim in alternating rhythms that still look uncanny. Some variable stars do not settle for one steady beat. RV Tauri stars rise and fall in a pattern where deep and shallow minima alternate, creating a brightness rhythm that feels almost like a heartbeat with an irregular echo. When plotted over time, their light curves look so distinctive that once you know the pattern, you never quite forget it. These stars are thought to be in a brief and unsettled phase after the red giant stage, on their way toward becoming hotter remnants surrounded by old expelled material. That transitional status gives them much of their intrigue. They are unstable because they are in between identities. Some also show long-term changes superimposed on the alternating pattern, which makes them feel even stranger, as though one rhythm is nested inside another. RV Tauri stars are a wonderful reminder that a star's final chapters need not be neat. They can be wavering, layered, and oddly beautiful, as though the star cannot quite decide how to leave. Cepheids are not rare, but rare versions help refine cosmic distances. Ordinary Cepheidae variables are already among astronomy's most important stars, because their pulsation periods reveal their true luminosities, and let astronomers measure distance across the universe. But some rarer Cepheid variants make that story even richer. Unusual pulsation modes, low metal content, or membership in eclipsing binary systems can give astronomers extra leverage to test and refine the method. These stars matter because cosmic distance measurement depends on trust, and rare Cepheid cases let scientists check the ruler against itself. If a Cepheid also belongs to a binary system, for example, its mass and size may be constrained more directly. If it pulsates in a less common mode, it can reveal how internal structure affects the relationship between period and brightness. What sounds like an obscure detail ends up shaping one of astronomy's grandest tasks, measuring the scale of the cosmos. A slightly odd Cepheid can help sharpen the ladder by which we estimate the size of the visible universe. Some stars flash because their surfaces are unstable, not their cores. Not every stellar outburst comes from deep nuclear drama. In some stars, the trouble lives in the outer layers. Surface instabilities can cause sudden changes in brightness when gas shifts, opacity changes, or thin layers become temporarily unable to hold themselves in balance. In compact stars such as white dwarfs, matter accumulated on the surface can ignite explosively without destroying the star beneath. In other cases, thin outer zones may drive brief pulsations or flashes that are more about atmospheric behavior than core evolution. This matters because it changes how we think about starlight. A brightening does not always mean the entire star has changed in a fundamental way. Sometimes the star is more like a great lamp with a restless outer skin, where the drama is local rather than central. That distinction is fascinating. The visible fireworks may be real and dramatic, yet the deepest interior remains comparatively unchanged, while the surface alone steals the show. Others change because a companion keeps disturbing their outer layers. Some stars would live quieter lives if they were left alone. In a binary system, however, a close companion can pull, heat, strip, or distort the outer layers in ways that make the star visibly variable. Tidal forces can stretch the star into an oblong shape. Passing gas streams can strike the surface and create hotspots. Irradiation from a compact partner can bake one side more strongly than the other, so the star changes appearance as it turns. In extreme cases, the outer atmosphere may be siphoned away altogether. What makes these systems so compelling is that the variability is relational. The star is not changing only because of its own internal physics. It is being continually modified by a neighbor's gravity, radiation, or hunger. That turns the light curve into a record of interaction. A star, in such a pair, is never fully alone with itself. Its visible behavior is partly the biography of a partnership written across the surface. The sky contains stars that beat, flare, fade, and erupt. It is easy to imagine the stars as fixed lights, distant and unchanging, because to the naked eye, most of them seem exactly that. Yet once astronomy began watching carefully and repeatedly, the sky transformed into a place of motion. Some stars pulse with slow, regular rhythm. Others flash in violent bursts. Some fade behind dust they create themselves. Others erupt through mass loss, collapse, or unstable accretion. The night sky turned out not to be a frozen pattern, but a vast field of ongoing behavior. That realization is one of the great emotional shifts in astronomy. A star is not just a point. It can be a clock, a warning, a flare, a disguise, or the aftermath of some older collision. Each kind of change reveals a different layer of physics and history. Once you understand that, the heavens stop feeling static and start feeling active. The stars are not merely present above us. They are doing things. Rare stars make the universe feel less fixed and more alive. The more you learn about unusual stars, the harder it becomes to see the cosmos as a silent arrangement of permanent lights. Rare stars shift that feeling completely. They remind us that the universe is full of change, risk, pressure, and improvisation. A star can cannibalize a companion, hide in its own dust, fling matter into space, or collapse into an object stranger than common sense can comfortably allow. Even death is not always a clean ending. It can leave behind clocks, magnetic beasts, crystalline remnants, or systems still interacting long after the original star has changed form. That is why rare stars have such emotional force as well as scientific value. They introduce biography into the sky. They make the universe feel eventful rather than decorative. Once the exceptions become visible, the whole cosmos seems more dynamic. The stars are no longer distant furniture. They are actors in long, unfolding dramas, and the night begins to feel charged with hidden activity. Some stellar oddities are seen only because modern telescopes arrived in time. For most of human history, the sky was observed with eyes, memory, and patience. That was enough to notice bright nova, mirrors changing light, or a great supernova. But many rare stellar behaviors are subtler, shorter-lived, or hidden in wavelengths human eyes cannot detect. Modern telescopes changed that completely. Space observatories revealed X-ray binaries and gamma flares. Infrared instruments exposed dust-shrouded stars and pinwheel spirals. Wide field surveys began revisiting the same sky night after night, catching transient outbursts that older astronomy would almost certainly have missed. In that sense, discovery has depended not only on what the universe is doing, but on whether our technology matured in time to witness it. That thought is thrilling. Some rare stars were always there, performing their strange acts in silence, while humanity lacked the senses to notice. The modern era did not create those objects. It simply arrived with better eyes, just in time to see their hidden performances. Others were hiding in old data until astronomers learned where to look. One of the most beautiful things in astronomy is that discovery does not always require a new telescope. Sometimes it requires a new question. Archives contain vast amounts of starlight gathered for one purpose and later re-examined for another. A spectrum once filed away as routine may reveal an unusual abundance pattern when compared with new models. A faint variability buried in a long light curve may suddenly matter once astronomers know what kind of rhythm to search for. Even entire classes of objects have become clearer only after researchers learned to connect scattered clues across old observations. This gives astronomy a wonderful sense of delayed revelation. The sky may have already told us something strange, and we simply were not yet ready to hear it. Then theory improves, computing gets stronger, or classification sharpens, and hidden rare stars begin stepping out of the background. The archive becomes a second universe, full of secrets that were observed long ago and only understood later. A rare star can teach more than 1 million ordinary ones. There is great value in the ordinary. Most stars are useful because they establish patterns, anchor theory, and show the common ways stellar life unfolds. But every so often, one rare object reveals a weakness in our understanding so sharply that it teaches more than countless routine examples combined. That is because science advances most dramatically where expectation fails. A single magnetar flare can challenge models of magnetic stress. One stripped binary can clarify how stars exchange mass. A peculiar pulsator can expose missing details in our picture of stellar interiors. Rare stars matter not because they replace the common ones, but because they illuminate the edges of the rulebook. They show where the theory bends, breaks, or becomes incomplete. That gives them unusual scientific leverage. One strange star can redirect whole areas of research by forcing better questions. In astronomy, the exceptions are not ornamental. They are often the places where the deepest learning begins. The shortest-lived stars often leave the loudest clues behind. Massive stars live with astonishing urgency. They burn through their fuel rapidly, push hard against their own gravity, and often end in dramatic ways compared with longer-lived stars like the Sun. Because their lives are brief, their rarest phases are fleeting and precious to catch. Yet, when they act, they tend to announce themselves loudly. Their winds carve bubbles. Their eruptions throw off nebulae. Their deaths create supernova remnants, neutron stars, and black holes. Even their stripped intermediate stages can flood their surroundings with radiation and unusual chemistry. That is one of the great paradoxes of stellar life. The stars with the least time often leave the boldest marks. Their biographies are short, but their signatures can last far longer than the stars themselves. This gives them a kind of amplified legacy. A massive rare star may vanish quickly by cosmic standards, yet the bubble, remnant, shockwave, or compact core it leaves behind can keep telling its story long afterward. Some rare stars exist for barely a blink in cosmic history. The universe has been making stars for billions of years, and against that backdrop, some stellar states are astonishingly brief. A star may spend millions of years in a calm main sequence phase, then pass through a rare transitional stage in a relative instant. A violent outburst, a contact phase in a binary system, or a highly stripped configuration may persist only for a tiny fraction of the object's total life. That brevity is part of why rare stars feel so precious. Observing one can be like catching a single frame from a long film, except the frame itself contains crucial information about how the whole story works. Astronomers depend on those brief chapters because they often reveal the most dramatic changes, the points where mass is lost, orbits tighten, or new remnants are born. A rare star can therefore be both temporary and essential. It may not linger, but it can tell us exactly how a long, ordinary history turns into something extraordinary. Stellar evolution is not one path, but a tangled wilderness. It is tempting to imagine stars following simple tracks determined only by mass. There is truth in that, but rare stars reveal how incomplete the simple picture really is. Rotation matters. Magnetic fields matter. Companions matter enormously. So do collisions, metallicity, and the timing of mass loss. Once those factors enter, stellar evolution stops looking like a single road and starts looking like branching terrain full of detours, crossroads, and dead ends. Two stars born with similar masses can reach remarkably different outcomes depending on whether they live alone, steal gas, merge, or lose their envelopes early. That complexity is not a nuisance. It is the reason the sky contains such variety. Rare stars are the landmarks inside that wilderness. They show what happens when the path bends sharply. Instead of a universal script, the universe offers a web of possible lives. The more carefully astronomers look, the less stellar evolution resembles a march, and the more it resembles a wilderness. The strangest stars usually owe their existence to companionship and conflict. A surprising number of stellar oddities turn out not to be solitary marvels, but the results of close relationships gone complicated. A star steals gas and becomes unstable. Another loses its outer layers and reveals a hidden core. Two stars merge and create an imposter youth. A compact remnant spins faster because a companion fed it long ago. Again and again, the strange outcomes arise because one star interfered with another. That gives rare star astronomy a wonderfully dramatic quality. The weirdest objects are often not weird, because they were born different, but because they lived in systems where gravity turned closeness into transformation. Companionship in the sky is not gentle. It can mean distortion, theft, heating, engulfment, and eventual destruction. Yet it also creates some of the richest phenomena astronomers can study. Many rare stars are the products of entanglement. Conflict does not merely damage them. It gives them identities that solitary stars might never attain. Many rare stars are really stories about pairs, not singles. If you tried to explain unusual stars using only solitary evolution, you would miss a huge share of the real drama. Binary systems reshape the sky. They let stars exchange mass, alter rotation rates, strip outer layers, ignite surface explosions, and produce compact remnants with strange companions still attached. What looks like a peculiar individual often turns out to be the visible half of a relationship. That is why rare stars so often come with hidden context. The object may seem baffling until astronomers discover an orbit, a donor star, or chemical evidence of past mass transfer. Suddenly, the mystery becomes a story about two lives influencing one another. This is a powerful shift in perspective. The star is not just what it is alone. It is what the pair became together. Binary astronomy teaches that some of the strangest lights in the sky are not single biographies at all. They are joint histories, compressed into one extraordinary visible result. The universe keeps making exceptions where astronomy once expected rules. Science needs rules. Without them, there is no pattern to test, no theory to improve, no order to discover. Yet some of astronomy's most exciting progress has come when the sky refused to fit the clean categories we expected. Rare stars are full of such exceptions. A pulsar changes class. A cluster contains stars of the wrong apparent age. A compact remnant behaves in a way no simple model predicted. A hidden binary turns an ordinary spectrum into evidence of something much stranger. These objects do not destroy the rules. They refine them by showing where they were incomplete. That is what makes rare stars so intellectually thrilling. They reward curiosity rather than certainty. Every exception is an invitation to ask, what hidden factor was missed? What interaction mattered? Or what physical regime has not yet been fully understood? The universe is not chaotic, but it is more inventive than our first drafts. Rare stars are where that inventiveness becomes impossible to ignore. Rare stars remind us that death can be as creative as birth. When we think about stars, we often focus on their formation, the drama of clouds collapsing and new light igniting. Rare stars reveal that endings can be just as generative. A dying massive star may sculpt a nebula, enrich space with heavy elements, and leave behind a neutron star or black hole. A sun-like star may cast off a glowing shell and become a white dwarf that cools into crystalline matter. A binary death spiral can create nova, stripped remnants, or merged objects with new identities. In each case, the final chapters do not simply erase what came before. They produce new forms, new chemistry, and new physical laboratories. Death in stellar astronomy is often an act of transformation rather than disappearance. That is one reason these objects feel so profound. They show that destruction in the universe can also be a form of creation. The end of one stable state becomes the beginning of a stranger and often more revealing one. The oddest suns in the sky are often the most revealing. A very strange star is rarely just a curiosity pinned to the edge of a catalogue. More often, it is a clue. Its odd brightness, chemistry, timing, or companionship points directly towards some process, but would be harder to see in a more ordinary object. A rare star can expose hidden fusion layers, reveal how mass transfer works, test quantum support, challenge models of ultra-dense matter, or refine the ways we measure the universe itself. That is why the oddest objects often become scientific treasures. Their weirdness is not a distraction from the truth. It is the place where the truth becomes easiest to see. Ordinary stars teach us the rule. Rare stars show us the mechanism under strain. They are the pressure points where astrophysics reveals its deeper structure. So when astronomers become excited about a truly peculiar star, it is not because they love novelty for its own sake. It is because the weirdest objects often explain the most. Once you notice rare stars, ordinary starlight never feels ordinary again. That may be the most lasting change these objects produce. After learning about pulsars, magnetars, blue stragglers, stripped stars, pinwheel binaries, and crystalline white dwarfs, it becomes impossible to look at the night sky in quite the same way. The stars no longer feel like a single category. Every point of light becomes a possible history. Some may be stable and familiar. Others may be hiding companions, shedding matter, pulsing in silence, or carrying the aftermath of some long past collision. Even the apparently normal stars start to feel richer, because now you know how many unusual pathways stellar life can take. Rare stars do not only make the strange ones more fascinating, they deepen the entire sky. They turn starlight into biography, physics, and possibility all at once. Once that shift happens, the heavens stop looking like a backdrop. They become a crowd of stories, and even the calmest light begins to feel charged with hidden drama. Tonight, we wandered among some of the strangest stars the universe has ever made. We passed through clouds shaped by stellar winds, through spirals of dust turning around hidden companions, through stars that pulse, flare, steal, collide, and slowly transform into something far stranger than the steady lights we usually imagine. We visited dense remnants where matter is crushed beyond reason, magnetic stars that can lash out across the galaxy, and ancient imposters hiding in old clusters with borrowed youth still glowing on their surfaces. And now, after all of that distance and fire, perhaps the sky feels a little different. Not empty, not silent, but full of lives unfolding in darkness. Some brief and brilliant, some slow and fading, some hidden beneath dust or folded inside binary systems, or waiting at the edge of an ending, but will one day reshape everything around them. So now, let all of that begin to drift. Let the strange stars grow softer in your mind. Let the bright remnants dim into the background. Let the spirals, the pulses, the flares, and the fading lights settle into a calm and distant glow. If you enjoyed this journey, you might like to subscribe, leave a thought below, or return for another sleepy exploration soon. And if you happen to still be awake, there should be another video waiting for you on the screen now, ready to carry you a little farther into the night. But for now, just rest. Let your breathing slow. Let your body grow heavy, and let the last of these faraway stars fade gently above you until there is nothing left to do and nowhere left to go but sleep. Sleep well, and good night.